Today I'm going to be talking about the results of my project to enhance GPS localization in urban settings. So GPS doesn't work very well by itself in certain areas. For example, this data was collected by a GPS watch in downtown Seattle. The blue path here is the path that was actually traversed, and the red path is the raw GPS measurements for the same trial. And as you can see, the error nears 100 meters at some points, which is quite bad. One of the main sources of GPS positioning error in urban areas is multipath interference, which is where signals from GPS satellites reflect off buildings or other large structures, which confuses GPS-enabled devices. This is where my project comes in. The goal of my project is to improve GPS localization in urban areas by using known street maps. You've already seen this slide a few times, but I'll touch briefly on where I get my data. So data is loaded from a GPS watch and is parsed to kind of get the relevant information, namely time, latitude, and longitude. The relevant street map is downloaded from openstreetmap.org and is parsed to get into this format, which I'll talk about later, but it's basically a table of street segments. And then finally, a satellite image is downloaded using the Google Earth API. The actual particle filter implementation is familiar at this point. The most interesting parts are the motion model here and the particle weighting algorithm, which I'll talk more about in the next few slides. My particle state includes position, heading, as well as the particle weight. So looking at the motion model, it's essentially a pseudo-random walk with a perturbed yaw. The yaw perturbation is described by this PDF on the top right, which is highly weights staying straight or turning to the left or right by 90 degrees. The speed probability density function here was derived from walking velocity measurements and tuned for performance. Next, I'll talk about the particle weighting step. So this is the information that I get from openstreetmap.org. When I download information for a particular region, I get a set of nodes, which are these white dots, as well as the relationship between them, so whether they are members of the same street. So I first have to parse that information to get into this format here shown on the left, which is a street segment table. So for each street segment, it's defined by the adjacent nodes and their coordinates, as well as a street width. So certain streets are wider than others, and this is taken into account in this algorithm. Once I have that all that information, I can basically define a region around these street segments, which are more highly weighted, meaning it's more probable that a walker or a runner is staying within this green region rather than walking into the middle of a city block where there are houses or other structures. So I can find this region using information in this street segment table. Now, how I actually calculate this is shown on this slide. For every particle in the particle set, the distance to the nearest street segment is calculated using these equations. So for example, this green dot here is a known particle state, and this black line is one of the many street segments, and I can calculate the distance between the particle state and this street segment using these equations. And then I find the minimum distance, so I do that for every street segment and find which street segment is closer and then just use that one distance to the nearest street. Finally, the particle weight is determined using these two equations. So the plot on the left here relates the relative particle weight to the distance to the nearest street. So as you can see, if the particle is within half of a street width, the particle is weighted very highly, and then that decays quickly as you leave the street. On the right, we see a second graph where, again, if the most recent GPS measurement is very close to the particle state, then the particle is weighted very highly. But as those two measurements are farther apart, then the particle weight will decrease. And the overall particle weight is just the product of these two functions. In terms of experimentation, as I said before, I collected data using this GPS watch. This is a Garmin Instinct, I believe is what it's called. For absolute truth, I actually walked on 3 routes, and I took a video as I was walking. So then after the fact, I could go back and timestamp exactly when I crossed each intersection and then interpolate that data to match the time series from the GPS watch. And I conducted 3 main routes in 3 different kind of types of environments, residential, commercial, and urban, which I'll talk about in the next few slides. This is a pretty typical view for the residential kind of environment. This is a plot of the raw GPS measurements, the truth measurements, and the estimated position during this trial. And as you can see, the GPS itself and my filter match pretty well to the absolute truth. This is a plot of the error over time for the raw GPS and the estimated error, or the estimated position. And most of the time they track pretty well. Toward the end of the trial, the estimate actually got a little bit better, but not super significantly. This is a typical scene from the commercial environment. So there are some kind of high-rise apartments, some other buildings and shops, but no very large buildings. This is the same kind of plot as the one for the residential. As you can see, there are some locations where the GPS did a little bit worse because of these large buildings. So you can see over here, I was walking straight along the sidewalk, but because there's some high rises here, GPS kind of drifted. In this corner, you can also see the red line, the GPS deviated quite significantly from the blue absolute truth line, and the estimate did a little bit better, but not by a whole lot. This is shown in this error plot as well. Sometimes the estimate error was significantly lower than the GPS error, but other times the estimate was actually worse. And then finally, this last trial, which did not go very well, was a trial in an urban setting. So this is the Columbia Tower here, which is the tallest building in Seattle. A lot of skyscrapers in this route, and the GPS had absolutely no idea where it was. This is the same plot on one of the first slides. So the estimated position here was a little bit better, but it still was very confused. And this is because when the uncertainty in the GPS measurement is on the order of magnitude of a city block, then my algorithm, which basically snaps the particle to the nearest street, it doesn't have enough information to determine which street it's at. This is the plot for the error for that trial. As you can see at the beginning, the arrow is at 100 meters, and it gets better, but it's still much worse than either of the other two trials. This table summarizes the main findings of my filter. Again, I think there's a lot more tuning that can be done, but even with the relatively small amount of tuning that I did, each of the trials did have an improvement in the actual error, in the position error for all three trials. So it did best, the filter worked best in the commercial trial with a % improvement in average RMS error over the course of the trial of more than 20%, but the other two trials did not work nearly as well. In conclusion, known maps can marginally improve GPS localization accuracy, but for extremely GPS hostile environments like around skyscrapers, additional information is really needed for effective localization. There is a lot of potential improvements to this filter. For example, the motion model can definitely be tuned to different kinds of locomotion. So instead of just walking, it can be tuned to incorporate running as well, and maybe use information like the cadence measured by the watch to inform the motion model. And also, you can do tricky things like backtracking the most highly weighted particles, because all this is done in post-processing. These are my references, just the one that I presented on a few weeks ago, and I'd like to open the floor to any questions.